Hi there, welcome back. In this slice of physics, we're going to take another example with Coulomb's law. Once again, we're going to determine the net force on a charge from two other charges, but this is going to be a two-dimensional scenario where the charges are not in a straight line, so we need to use trigonometry to determine the net force. Okay, so here's the problem we're looking to tackle today. It says that charge A of plus 50 microcoulombs sits at the origin. Charge B of minus 40 microcoulombs sits on the x-axis 0.5 meters to its right, and charge C of plus 30 microcoulombs sits on the y-axis 0.4 meters above charge A. What is the net electric force on charge C? Once again, I've listed my solution steps or recipe over here. I've taken the same instructions from last time and just modified them a little bit to make it more generic. And I've got my equations for electric force between charges listed over here, as well as the electrostatic constant. So let's get started. The first step was to draw a picture. So here's charge A that sits at the origin, and it's plus 50 microcoulombs. Charge B sits 0.5 meters to its right, and charge B is minus 40 microcoulombs. And this distance here is 0.5 meters. And charge C sits 0.4 meters above charge A, and it's got a charge of plus 30 microcoulomb. And the question is asking for the net force on charge C, which would be the combined effect of electric forces from charge A and B on C. Our next step was to determine each of these individual forces on our charge of interest. In this case, charge of interest is charge C. So we need to figure out force of A on C and force of B on C, and we can do those two independently. When we're looking to figure out the force of A on C, we can completely ignore B, and when we're trying to figure out the force of B on C, we can completely ignore A. Now the force of A on C is a simple application of this equation. We know the electrostatic constant, we know the absolute value of charge A, 50 microcoulomb, absolute value of charge C, 30 microcoulomb, and the distance between them is 0.4 meter. And since we got a lot of practice in the previous two videos working with that equation, I'm not going to show you the work again and simply say that this FA on C becomes 0.8438 Newton. And I've carried a couple extra significant digits because this is an intermediate step, and I'll round only the final answer to the two significant digits that was in the question. So this equation gives us the magnitude of this force. Let's see what its direction looks like. For that, we got to go back to the picture. This force is applied on C, so I got to start my arrow at C. And next I look at the sign of charge C and A. They are both positive charges, so the force between them would be repulsive. And since A repels C, the force would be away from A. So let's show it like this, vertically up, and we'll call that FA on C. Now I do want to show the work for the force of B on C, since that's different from what we've been doing so far. So FB on C would be the electrostatic constant times the absolute value of charge B times the absolute value of charge C divided by the square of the distance between B and C. Now the distance between B and C will be this straight line over here. That's not given to us directly, but we see that that's the hypotenuse of a right angle triangle that we know the two sides of. So we can use our Pythagorean theorem to say that RBC is simply the square root of the sum of the squares of the other two sides. So this will be 0.5 squared plus 0.4 squared, and that gives us 0.6403 meters. And once again, I'm carrying a couple extra significant digits for intermediate steps. So back to this equation, I've got 9 times 10 to the 9 for the electrostatic constant. Absolute value of charge B, I can drop the negative sign. I got 40 microcoulomb, which is 40 times 10 to the negative 6 coulomb, times absolute value of charge C, which is 30 microcoulomb, so 30 times 10 to the negative 6 coulomb, divided by the square of the distance, 0.6403 squared. And that gives us 0.2634 Newton. Now this equation gives us the magnitude of the force. For the direction, we got to go back to our diagram. So the force is acting on C from B. So the arrow for the force has to start at charge C, and then we look at the signs. C is a positive charge, B is a negative charge, so B will attract C. So the force on C would be toward B. And then we look at the magnitudes of the previous force we showed, and this one, the current one, is about 1/3 of the previous force. So this arrow would be about 1/3 of the length of the previous one, and so like this. Now, since this is pointing at some angle to the horizontal and to the vertical, let's figure out what this angle is. So if I draw a horizontal line over here, I want to get this angle theta, which is the same as this angle theta. When you have two parallel lines being intersected by another line, the opposite interior angles are equal to each other. And I'll just show that work over here. So for this right angle triangle, I'm going to use my SOHCAHTOAs for the trigonometric identities. So this TOA part tells us that the tangent of an angle equals the opposite over the adjacent side. So that gives us tangent of theta equals 0.4 over 0.5. And when you solve for theta, you get tangent inverse 0.4 over 0.5, which in your calculator would be 38.66 degrees. Okay, so let's recap. We have finished step 2 to determine the individual forces, and we've also shown them as vectors on our charge of interest. So now we're left with the very last step. So the net force on C is the vector addition of these two forces. We can't just add the numbers, we got to add them as vectors. So to do that geometrically, I can grab B on C and drag its tail to the tip of A, and then the net force would simply be the arrow from the original tail to the final tip. So here's F net on C, which is what we're interested in figuring out. Now, while the diagram gives us an approximate sense of what it is, we need to work with some numbers to get the specific magnitude and direction of that force. And as discussed in a previous video, the easiest way to add vectors numerically is to work with their components. So I want to take the original FA on C and FB on C, break them into their x and y components, add the x components together, add the y components together, and that'll give us the components of the F net C. So let me set up a little table over here to help with that. I have FA on C, and I got FB on C, and I want to figure out their x components and their y components. And by the way, here's my x-axis and here's my y-axis. Now take a look at FA on C. All of it is acting along the positive y-axis, so it has no x component. That's simply 0. And the y component is simply the original vector 0.8438 Newton, all acting in the positive direction, so let me put a plus. So for FB on C, I want the x component and y component. And let me reproduce that over here. I've enlarged FB on C in this diagram, so I got FB on C acting like that. I know its magnitude, it's 0.2634. I know its direction, it acts at an angle of theta, which is 38.66 degrees below the x-axis. And so its x component is this guy over here, FB on C x, and its y component is over here, FB on C y. So given this right angle triangle, I know the hypotenuse, I want the adjacent to the angle, so this is A, and I want the opposite to the angle, which is O. And going back to our SOHCAHTOAs, we can see that FB on C x component of it is the adjacent, so I need the cosine function, so that would be FB on C, the full vector hypotenuse times cosine of theta, which in this case is 0.2634 times cosine of 38.66 degrees, and that gives us 0.2057 Newton. And similarly, FB on C y component is opposite, so I need the sine function for it. So FB on C y component would simply be FB on C, the hypotenuse, times sine of theta. And in this case, that would be 0.2634 times sine of 38.66 degrees, which is 0.1 0.1645 Newton. And when we record those values in the table, we have to use the right sign. In this case, the x component is positive because it points to the right, but the y component is negative because it points down. So I got FB on C, the x component as plus 0.2057 Newton, and the y component as minus 0.1645 Newton. Okay, now that we have the components of these vectors, I can get the F net on C, its x component and y component, by simply adding these numbers. And so I'd get plus 0.2057 Newton as the x component of the net force on C. So this guy, this vector over here that I showed, its x component is simply 0.2057 Newton. And its y component, when I take 0.8438 and add to it minus 0.1645, I would get plus 0.6792 Newton. And going back to our drawing, that makes sense. We have positive x component and positive y component. The y component is larger than the x component, so all of that ties in nicely. Our last step is to figure out the magnitude of this vector and its direction. So to do that, I'm going to clear a little bit of room over here and continue the work. Okay, let me show the x and y component of this F net C. So I've got x component pointing like this in the positive x direction of 0.2057 Newton, and I got the y component pointing straight up like this, and that is 0.6792 Newton. The net force is simply the vector sum of these, so if I slide F net x to the top, it'll look like that. And my net force that I want is this guy over here. So this is F net C, which we're interested in finding. Well, once again, I know that this is a right triangle over here, and I know its two legs, and I want its hypotenuse. So F net C, the magnitude of it would simply be the square root of the sum of the squares of the other two sides, and that is 0.709 or 0.71 Newton. This is the final answer, so I'm coming back to two significant digits. And to specify its direction, let's call this angle here as alpha to differentiate it from the theta we were using there. And then for alpha, I got an opposite side over here in this right triangle, which is 0.6792, and an adjacent side, which is 0.2057. So alpha would be simply be tangent inverse. Since I know opposite and adjacent, I use the tangent function. Tangent inverse of the opposite, 0.6792 divided by 0.2057, and that, according to my calculator, is 73 degrees, down to two significant digits. So that's our final answer. We've determined the net force on charge C as the vector sum of the other two. So this magnitude is equal to 0.71 Newton, and it acts at an angle of 73 degrees above the positive x-axis. This slice of physics tackled another example of determining the net electric force on a charge from two other charges. The process and the method we followed was the same, but this one was a lot more elaborate in terms of using trigonometry to figure out the distances and the components of the forces and their addition.